Let's begin our very exciting look at free body diagrams, shall we?
Yay.
Okay. Let me just zoom in a little bit here to make it a bit more readable. That might be too much. Free body diagrams, also known as FBDs, are simplified representations in a problem of an object, the body, and the force vectors acting on it. This body is free because the diagram will show it without its surroundings, i.e. the body is free of its environment. So in other words, it's a really, really simplified diagram of what's going on, and then you throw the forces in there. And you guys have seen these already probably in grade 10. You probably just weren't calling them free body diagrams. So this eliminates unnecessary information which might be given in a problem. Let's take this figure to be a pictorial representation of a situation. A sled on snow with horses pulling it. And there's a picture right there, right? First, we're going to represent the sled. The body in our problem is a really simplified figure, a square resting on a flat surface. Traditionally, they use squares like this. Some textbooks just use like a dot to signify the object. Okay? It's really up to your personal preference there. In this tutorial, we will review some of the main forces which you will encounter in physics and discuss their contribution to an FBD. So we'll start with gravity. The first force that we will investigate is not due to gravity, and we'll call it the gravitational force. Ooh, that's a stretch. We know that acceleration due to gravity upon Earth is approximately 9.8 meters per second squared, and the force by Newton's second law is Fg equals mg. Now this Fg, F means force, and then the G stands for, the subscript is gravity. I quite often call it weight force, because it's really, I quite often call it FW. So if you want to add that in there, that might be a good idea. That's just a habit that I've gotten myself into. I think you can see it over here on the right side as well here too. FMG is equal to FW. Okay? So the big F just signifies force, and then the subscript sort of indicates what type of force it is. Where G is, of course, the acceleration due to gravity, and M is the mass of the carriage. Let's add this to our diagram. Note that the force vector labeled Fg or Fw points downward, as this is the direction which the gravitational force acts. Note that this force is also commonly called weight. The weight mg is different from our everyday use of the word weight, which is known in physics as mass. When someone says, how much do you weigh? And if you answer in pounds, you are actually giving an actual weight, because pounds is a unit of force, actually. So when you say you weigh 150 pounds, it's really 150 pounds of force, okay? If you give your weight in kilograms, then it's actually a mass, although people commonly will convert between the two, and it's really not technically correct. Only Sheldon Cooper's going to get too upset. Okay, normal force is one that prevents objects from falling into whatever it is they are sitting upon. It is always perpendicular to the surface, and if you have a highlighter, I encourage you to highlight. Why do I never have a highlighter when I want one here? Perpendicular. Oh yeah, that's what that does. Perpendicular. Normal means perpendicular to the surface with which it has contact. For example, if there's a crate on the floor, then we say that the crate experiences a normal force exerted by the floor, and because of this force, the crate does not fall into the floor. The normal force on the crate points upward perpendicular to the floor. It's called the normal force because normal and perpendicular mean the same thing. Now, this is sort of important. You might get the impression that the weight force, which is down, is always going to be counteracted by the normal force, which we sometimes put, do you guys know what that symbol means?
Perpendicular.
That perpendicular symbol. We sometimes write it like that. We sometimes write it as Fn. Either one is perfectly acceptable. Most of the time, the weight force is going to be perfectly balanced by the normal force. Can you think of a situation where that might not be the case?
It's not
The question was, Joy, when would it not be perpendicular? You can't answer with when it's not perpendicular.
When it's parallel. Am I not right, though?
How about I'll draw this.
Like an example.
I'll draw this a little better. You could say when the object is sitting on a
Incline.
Thank you. That's a better answer. An incline. When the object is sitting on an incline, then the weight force is down, but the normal force, you'll notice, is not up. The normal force is not opposite to the weight force. It is in fact, if I could just continue that right down to there, it is in fact perpendicular to the plane that it is sitting on. The normal force is perpendicular to the plane that it's sitting on. So if it's a steeper slope, then what would it be like? Well, the normal force would be like that, wouldn't it? And the weight force would be down. If they're up and down like this, and they're equal, then what would the net force be? 0. But Chris, if it's at a steep angle like this, and you add those vectors together, do you get a net force of 0? No, you do not get a net force of 0. Without getting into components and a whole bunch of rigmarole, can you use your brain, your intuition here a little bit, and tell me which direction you think the net force would be? Which way does the box move? Down the ramp. Which way is the net force? Down the ramp. Absolutely, okay? So when you add those two together, and really all I'm going to do is take these and, oh, I can't do it. Put them tip to tail. I'll draw it in red so that I can move it. Tip to tail. Oh, yeah. Vectors. Down the ramp. No, what you mean? You mispronounced it, Hannah. It's yay! That's how you pronounce it. Oh, yes. What fun we're going to have. Yeah, but that would help. Let's add the normal force. I sort of went a little bit forward there. I got a little bit carried away. Yeah, so I had a little bit of a net force on me, and I accelerated into the future a little bit there. Let's add the normal force to our FBD and represent the normal force with the letter Fn. And if you prefer to write it, if you want to write it F perpendicular, you go right ahead. Friction, related to the normal force, is the frictional force. The two are related because they are both due to the fact that the body is in contact with the surface. Whereas the normal force was perpendicular to the surface, the frictional force is parallel. And therefore, the normal force and the friction force are always perpendicular to each other. Furthermore, friction opposes motion. Does there have to be motion for there to be friction?
No.
Why do you say no so boldly, Steve?
Because yeah.
Could you expand on your explanation a little, Steve?
Well, if something's already touching the ground, there must be friction.
Give me an example where you might push on something and there's friction and the thing doesn't move.
If it's really, really heavy.
Exactly, if it's really, really heavy. Like, say, my big filing cabinet full of old exams and stuff. If I just push on it sort of weakly, it doesn't move, does it? How come? Friction. Right? But if I push hard enough, then I'm going to overcome friction. Okay? So friction opposes motion. It's not always opposite to the motion, because there might not be motion. Friction is divided into two types, static and kinetic, and we're going to talk more about those in the future. That's not really the concern of today. These are represented by FF, which with a further subscript for static friction and a subscript for K for kinetic friction. In other words, FFS and FFK.
I put two F's.
Well, the big F is for force. The little f is for type of force, friction. What type of friction force? S. I don't get too excited about that. Don't worry about too much about that. As its name suggests, static friction occurs when the body is not moving. The word static means not moving, like static electricity, right? When you rub the balloon on your head, that's kind of electricity. Static electricity, right? There's no current there. You're not going to get too much of a zap, right? Current electricity is when you stick your finger in a socket. That's the wrong kind. As its name suggests, static friction occurs when the body is not moving with respect to the surface. It is the force that makes it difficult to start something moving, like me pushing the filing cabinet. Static friction. On the other hand, kinetic friction occurs when the body is sliding over the surface. Okay, so if I get my filing cabinet up moving, now it's what we call kinetic friction. Is it the same amount of friction? What do you think? To get something moving, excuse me, how's the friction like at the start compared to as you get something going?
It's pretty tough, right?
Quite often, static friction is much more than kinetic friction. Not always. Of course, rolling objects experience friction as well. Rolling friction is something entirely different. You can safely not worry about rolling friction for your high school physics courses. Okay? Anytime something's moving, we're going to assume it's sliding. Rolling friction is a little bit tricky. Okay? So we'll just leave that aside. This is the force that causes the object to slow down and eventually stop. Friction is usually approximated as being proportional to the normal force. In other words, as Steve pointed out, really heavy things, which would have a really big weight force, would have to have a really big normal force, and if the normal force is big, then the friction force is also big. Heavy things have a lot of friction. That's what it boils down to. The proportionality constant is called the coefficient of static or kinetic friction. Now, here's my favorite Greek letter. The coefficient is represented as mu s. That's what that funny looking symbol right there is. It's not so good on the screen because it's like a PDF kind of thing. But what it is a Greek U, it's a Greek M. It's like a U, like that, but it's got a tail on the front. Okay? If all you want to do is write a U, go ahead. But really, it's just instead of that, it's just with the tail on the front. Okay? So it's the Greek letter mu. M. Mu s is for static friction. Mu k is for kinetic friction. Mu is generally, I hesitate to use the word always, generally less than 1. If you get a mu value bigger than 1, that's a lot of friction. The numerical value of mu depends upon the nature of the surface with which the body is in contact. And more on that like in a couple of days. Okay, this is just sort of introduction. Mu. Okay, so this object here, I've got normal force up, I got my weight force down, I got my friction force to the left. Which way is this object moving? Trick question. That thing right there, that object that I've got the highlighter pointing to, which direction is it moving? Who says to the right? Hands up. Right hand up. Just Anderson. Oh, a couple others, okay. Who says it's moving to the left? Even less people. Some people think it's not moving at all.
Trick question.
Okay. I guess I'll give you a third option. Is the object moving? Hands up if you think it's not moving.
It could be moving or it could be not moving.
Oh, actually, that's a good answer. Is that maybe I do need to have a fourth option?
You have too many trick questions.
Yeah, this is tough, right? Okay, well, let's deal with all the possibilities. Could it be moving, Anderson? You say it's moving, right?
Yeah.
Does it have to be, or are you saying it could be?
It doesn't have to be.
Doesn't have to be, it just could be. He's right in that it certainly could be moving, right?
Yeah.
Because if it's moving to the right, which way is friction? Opposite. How come there's no arrow on there showing it's moving to the right, Mr. Bennett? Because it's not a picture showing movement, it's a picture showing forces, right? And if it's already moving, we don't need a force to keep it moving.
Yeah.
I gave it a big shove and it's sliding across the floor. And this is doing what? Slowing it down. So it certainly could be moving. Okay, well, let's deal with the fact now. Does it have to be moving?
No.
If it's stopped, if it's just sitting there, there's my chair, doesn't weigh very much, but it's just sitting there. Is it experiencing any friction? How so? So if there was no friction, it would do what? But it's already staying there.
Yeah. You're right.
In other words, could this object be stopped? Like, could it be sitting at rest? No. Friction only occurs when there is a force trying to produce a movement. You're right. If I just push gently against the filing cabinet, is friction holding it in place? Yes. Am I pushing on it? Yes. Are the forces balanced? Yes. But if I don't push on it, does friction push? I kind of liken it to being a teenager. It only does exactly how much it actually needs to. Not one speck more. No, I get a couple of smiles out of that. Of course I'm joking, right? It doesn't do any more than it needs to. I'm just barely touching it, not even close. Is it doing anything? Not until I do what? Touch it. When I touch the filing cabinet, then friction kicks in. Doesn't do any more than it has to. I apologize to all teenagers in the room if I offended you. Did I offend anybody?
Is there like a,
You
is there like a limit to how much friction you can apply?
Ah, is there a limit? Well, of course, that's that static friction. Because if I push really hard, friction can't be as strong as me, right? I will eventually overcome friction. There is a limit to how much friction, and it depends on how slippery the floor is, right? Like if I put motor oil underneath, what would the friction be like? A whole lot less. That's the whole idea of motor oil, right? If I put sand underneath, a lot more friction. So it depends on what's underneath it too. Okay, so in this case here, Anderson and whoever else agreed with him, Emma maybe and one other, I can't remember, Braden, I think maybe. Yes, this object must indeed be moving. Okay, it must be moving. How come? Because why? What's the net force here? Zero. It's not zero. These ones balance, but clearly there's a net force this way, right? So yes, it is moving, and quite likely slowing down. Okay, push and pull. Another force that may act on an object could be any physical push or pull. This could be caused by a person pushing a crate on the floor, a child pulling on a wagon, or in the case of our example, the horse pulling on the carriage. We will label the applied push or pull. I like to use the letters FA, applied force. There could be more than one applied force. In those cases, you might label them FA1, FA2, and I've just seen F1, F2, and so on as well, right? So FA1, FA2, F1, F2, that kind of thing. Okay, applied force. Tension is what you're feeling right now, right?
Yeah.
Mm-hmm. Tension in an object results if the pulling force acts on its end, such as in a rope used to pull a boulder. If we say that our carriage is being pulled by a bar, by the horse at its front end, then we can add this force to our FBD. And there we have it. All the forces acting on our carriage have been labeled in this figure. This is the complete FBD for our problem of a carriage being pulled along a road. There it is right there. All the forces are labeled on there. Is there a net force?
Yes.
Which direction, Joey? To the right. These ones balance. These ones do not. And so my overall net force is to the right. Yeah? Nod, say yeah, good. Okay, here's another one. We'll do through this one a little quicker here. This is a sled. The child next door wants to take his German shepherd named Spot for a ride on a sled. He chases Spot, who's running away while dragging the sled behind him. What forces are acting on the sled? Okay, so let's consider each about force in turn. Since the question does not state otherwise, we will assume that it's happening on Earth. That's a pretty safe assumption. Unless otherwise stated, assume things happen on Earth. So gravity is a force acting on the sled. The gravitational force FMG vector points downward. So let's draw that one in. You've got the box. Let's draw FW here. You can draw it emanating from the center. Some places prefer it to be from the edge. I really don't care. Weight force, down. The sled is being dragged on the ground, which we can take to be another surface. This surface exerts a force on the sled, preventing it from falling into the ground. Thus, there is a normal force on the sled. Those two arrows should be exactly the same length long. Will I get out my ruler and measure to the nearest tenth of a millimeter? No. Will I eyeball it to see if it's within about maybe 2 millimeters of each other? Yes. And if it looks like it's off, then I'll get my ruler out and I will measure it. Okay? And if you're off by more than 3, then I'll probably deduct the mark. I'm not going to get too excited about it. Like if you can't get it close enough within 3 millimeters by sort of, just drawing it freehand, then you're going to have to practice. Because the sled is in motion and the surface with which it has contact is not frictionless, then there is kinetic friction. How do we know it's frictionless? It doesn't say, it says dragging. You sometimes have to use your best judgment here. If it says dragged on hard packed snow or ice, then those are code words for no friction. If it says loosely packed snow or deep snow or gravel or something like that, you're right. There's still going to be some, right? So no friction here. The child is pulling on the sled, so there is a pull force. This pull may or may not be parallel to the ground, but that is an angle shown in the drawing. So it doesn't have to be sideways. It could actually be like this, an applied force up. Now, without getting too far ahead of myself, because it's sort of up at an angle there, that does funny things to the normal force. It does funny things to that force. We'll get into that. Okay, is that good? Has everybody got that drawn in there on theirs as well? That's all we're doing today is just drawing. Oh, I'm sorry. That's not frictionless. You're right. So I sort of skipped over that one, didn't I? So the friction is like this. Thank you, Keelan. Does it have to be to the left? No, it could be to the right, but then the applied force would have to be the other way. But we tend to think of things moving from left to right, just because of the world we live in.
So with the friction, it could be like any length, right?
Well,
Less specified.
it couldn't be longer than this one because then it wouldn't be moving, right? So because we know it's moving, this actually has to be shorter. Technically, Steve, it has to be shorter than this part because it has to be balanced by that. But we'll get into that. Good question. Okay, Dot and Spot. Spot, the German Shepherd, is being walked by his best pal Dot, the Siamese cat. Actually, Dot is pulling Spot across the ice rink, code word, and disturbing the neighborhood hockey game. What are the forces acting on Spot? Since this is taking place on Earth, we can assume a gravitational force mg on Spot. Because Spot is on the surface of the ice is exerting a normal force on him. We assume the ice is frictionless. There's that code word.
And the pull.
And the pull. And is that on my next page here? Yes, the push or pull may be misleading. While it's true that Spot is being pulled along by Dot, this is not the force acting on Spot. This is because Dot is actually pulling on the rope. The rope, in turn, through its tension, exerts a force on Spot. I think they're splitting hairs there, and I'm not going to worry a whole lot about that. They want you to label it FT or just T for tension. I'm perfectly happy with applied force.
Does it have to be on an upward angle?
We don't know. It doesn't say, right?
Okay.
Yeah. These are just sort of examples, right? If I gave you a question like that, I would give you an angle. Yeah. I'm just showing you that that's possible. Okay, last one here. King Kong. Climbing the Empire State Building, King Kong peeks into one of the corporate windows and sees a poster with Tarzan swinging from a vine. Our furry friend decides he'd much rather be swinging from vines instead of hanging around outside of skyscrapers. When King Kong is swinging from a vine, what forces are acting on him? King Kong has been reduced to a box. On Earth, weight force. The overgrown gorilla is not in contact with any surface, so there is no normal force. Again, he's not in contact with any surface, so neither static or kinetic friction is exerted on him. Steve is asking about air friction. There could be some air resistance. If we assume he's sort of swinging from left to right, you might see a small amount of air resistance if you choose to add that in there. Most of the time in grade 11 physics, we assume the air resistance is negligible. What is holding this ferocious beast up in the air? The vine. And what kind of force is that? That would be tension. F air. So there is some tension in the air.
Would it have to be equal to the other one?
It would have to be equal to it, wouldn't it? I'll say approximately equal to it, because it kind of depends on where he is in the path, too. So, well, yeah, that's a little bit more advanced. Okay, King Kong has had enough of monkeying around. Has returned to the Big Apple. Once again, he's up to his tricks with the Empire State Building, only this time he has taken the elevator instead. While he's riding up to the top of the building at a constant speed. Is that important? Yes, it is. What forces are acting on him? On Earth again, weight force, normal force. Anything else? He's riding upward, right? No sideways acceleration. That's it. So
what does the constant speed have?
What does the constant speed have to do with it? Good question, Steve. What would it look like if I didn't say constant speed? What if I said he's accelerating towards the top of the building? What would have to be different? Yeah, this one would have to be bigger, wouldn't it? Right? Because the net force has to be up, right? He's accelerating up. There has to be a net force up. You would quite likely, some books, I wouldn't get too excited about it, but some books would insist, let me see if I can get that back to the right size. Some books would insist on a normal force like that, and then another force, the overall accelerating force, right? And those two combined together would give you a net force up, right? Some books would put it like that. Some books would just have this force bigger, that's all. I just give it.
In our diagram, shouldn't the normal force be larger? So what's going on?
If it's going at a constant speed, it should be, that one should be deleted. If it's going at a constant speed, it should be exactly the same. Because remember, when the net force is 0, what does it do? Keep moving at a constant speed. Think about when you get in an elevator, okay? And not the kind we got in school, like I mean like a fast one, right? What does it feel like right when you first start moving? You sort of bend your knees a little bit, right? Like there's a big push on you. And then once it gets going, then what? That push, it's like standing on the floor kind of thing, right? Constant speed, that's why. Okay, I think I'm done yakking. What do you guys have for your next page? I think you have 10 to try, am I right?
Practice questions.
Okay, so there are 10, this little bit of text at the top is basically what I just taught you. There are 10 practice questions, 11 practice questions there. Take 11 minutes, and we'll check back then, and I'll give you some answers. Alrighty, number 1, a book is at rest on a tabletop. The diagram of the force acting in the book. Well, this is pretty simple, isn't it? It would just be weight force, normal force. Do you need to draw the table in there?
Yeah. No.
I don't technically think you do need to. I don't think you do. Some people like it, just a visual thing, but the whole idea of free body diagram is to remove all the distractions. So, not too big of a deal to put in, not too big a deal if you missed it. Okay? A girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes. Diagram the force acting on the girl. This time, of course, she wouldn't have a tabletop. She would have a weight force. Now, there are 2 ropes. Does that matter? Well, you probably should have 2 identical ones like this, labeled FT. If you combine them together, I'm okay with that. I get that. Technically, though, there's 2 separate forces.
So they're supposed to be equal to the weight force?
The total of them, Steve. If you put them, stack them on top of one another, yes, that's correct. Okay? An egg is free falling from a nest in a tree. Neglect air resistance. Diagram the forces acting on the egg as it falls. I think you should just have weight force, which means it's doing what? Not just falling, accelerating. A flying squirrel is gliding with no wing flaps from a tree to the ground at constant velocity. Consider air resistance. Diagram the forces acting on the squirrel. This time, for sure, you would not draw like a tabletop or anything like that. And in fact, your weight force would be perfectly balanced by the air resistance. If you want to write that as FF, because it's a type of friction, I'm okay with that.
Does the air resistance have to be going straight up?
I always get that question. Some people want to have it like this, right? Perfectly all right, except then what does that do to the net force? No longer 0. It says constant velocity, right? So that part would have to be not true then. In fact, what would happen is if the air resistance is up and to the left like this, then in fact your horizontal speed would actually slow down, right? Does that make sense? Like you'd actually be slowing down horizontally a little bit because there is that net force side.
When you think gliding, you don't just think
Yeah.
like slowly fall.
Yeah. Forward, right? Yeah, I get it. A rightward force applied to a book in order to move it across a desk with a rightward acceleration. Consider friction. Weight force, normal force. A rightward force applied in order to move it with a rightward acceleration. So we're going to have a large applied force, and we're also going to have a small friction force. How do I know the friction force is smaller? Because it says it's accelerating.
Do we need to draw the table this time around?
Sure. I'm not going to care one way or the other. I don't believe technically you're supposed to. Some people find it comforting.
Because isn't it just the object?
Yeah, it's supposed to just be the object. Okay? I'm not going to get too excited about it. Whatever you feel suits you best. Okay, what about number 6? A rightward force applied to a book in order to move it across the desk at a constant velocity. Consider friction, neglect air resistance. This time it's going to be exactly the same, except what? Yes, the weight force and the normal force should be equal, but because it's constant velocity, these guys should be equal. Applied force, friction force. Now, if you want to draw the table in, go ahead.
You want to get really fancy.
Correct. Kinetic friction force, FFK. Mr. Fancy Pants over there. Yeah, you go, Jake. Number 7, a college student rests a backpack upon his shoulder. The pack is suspended motionless by one strap from one shoulder. Diagram the vertical forces acting on the backpack. Yeah, you think so?
I think so.
Weight force down. It's one strap. FT. Number 8, a skydiver is descending with a constant velocity. Consider air resistance. Diagram the force acting upon the skydiver. Skydiver descending, constant velocity. Weight force, what would you call this one? Not normal. Air resistance, yeah. And they would have to be equal, right? Now, interestingly enough, and we'll get into this a little bit more, I'll just sort of give you a future thought kind of thing. When you jump out of, anybody skydived here? Nobody? Okay. When you jump out of the plane, do you fall at a constant rate the whole time? No, you accelerate, right? But eventually you reach terminal velocity, and that's not just a bad Arnold Schwarzenegger movie. Okay? What does terminal velocity really mean? Go ahead, Jake.
It's when the air resistance equals the force of gravity.
Yeah, and you stop accelerating, and in fact you just fall at a constant speed. So when they say terminal velocity, it doesn't mean that if you go that fast you're going to terminate. It just means that's the fastest speed you can go. You can't fall any faster. And it depends on your size, right? Depends on your size. If you've got a parachute, your terminal velocity is a whole lot less than if you don't. Then you will terminate. Number 9, a force is applied to the right to drag a sled across loosely packed snow. That's code for? There is friction with a rightward acceleration. Weight force, normal force.
Is the normal force and the weight force ever not equal each other?
Only on a ramp.
Right.
There is acceleration. FA, there is friction, loosely packed snow. Technically, you should be given numbers and there should be a scale, but most of the time, free body diagrams are just a visual aid to help you figure out the problem. Yeah, you know what happened to Ryan's friend when she YOLO'd? What happened, Ryan? I can't remember. When your friend YOLO'd. Chemistry class. Could no longer taste something? Or...
Oh, yeah. The Caroline didn't wear her safety glasses. Now she can't see why kids love the taste of Cinnamon Toast Crunch.
She should have learned. Yeah. YOLO.
YOLO.
A football, now here's my favorite one. A football is moving upwards toward its peak, having been booted by the punter. Neglect air resistance. Diagram the forces acting upon the football as it rises upward toward its peak. Naturally, the football game is occurring on Earth, so we have a gravitational force.
That's it.
Steve says that's it.
What?
No? What else do you want, Hannah? Oh.
Need applied force.
You need applied force?
Already applied.
Steve is 100% correct. Let me shake your hand, Steve DeRoche. I think you might be the first person that's ever jumped up and said that right away. That I can recall. I might call this the Steve DeRoche question from now on. I might even change it so it says, a football is moving upwards towards peak after having been booted by Steve DeRoche. Just to immortalize you. Excellent. There is no applied force because why? It's already been booted. My foot is no longer in contact with the football. I can no longer apply a force to it. But Mr. Bennett, how do I know that it's moving upward at an angle like that? You don't. And it doesn't matter because, again, this is a diagram showing the forces.
What if we decided to draw it the exact second foot?
It doesn't say that. It clearly says after having been booted.
So it's wrong, Jake.
Oh. Yes.
Excellent, excellent question. Gee, golly, I wonder if that might come back on an evaluation.
Sure hope it does.
A car is coasting to the right and slowing down. Diagram the force acting upon the car. Well, cars drive on the earth.
Most of the time.
Weight force, yeah, maybe not when you drive. Normal force.
Upper car.
Yeah. Okay, what else has to be here? It's moving to the right. It's coasting, though.
The friction has to be more than the...
It's coasting to the right and slowing down. So the friction force would have to point towards
A lot of friction.
the left. And is there applied force?
Yes, but it's smaller, maybe?
It says coasting. That implies to me that your foot's off the gas.
Yeah, but even still, the...
Yes, I know. Yes, I know. If you want,
It's a little bit...
if you were to do that, Jake, on a test, I would expect a little explanation here. Okay? I wouldn't put that force in there without some explanation that you understand what's going on with cars. Okay? Tomorrow what we will do is we will take some sample problems. We're going to use free bar diagrams to solve them and have a lot of math fun. Be sure that you're here for that.
That's